Well, good afternoon, folks. It's great to be with you. I'm coming to you from lovely downtown Bristol, Rhode Island. Kind of wish I was in Florida at the moment. The weather's not that great up here, but appreciate you coming to this Zoom presentation. It was planned to be in person, but life has intervened, and at least we have the technology available to be able to do this kind of thing. So this afternoon, we're going to talk about manufacturing and environmental issues that contribute to gelcoat cracking. Gelcoat cracking is a pretty ubiquitous situation that occurs across the composites industry. Almost no one who manufactures gel-coated products is immune from gelcoat cracking in one form or another, but it certainly can be minimized so that it's acceptable to the quality of your product and the perception of your customers. So that's what we're going to talk about today, the mechanisms for gelcoat cracking and what we can do to minimize the possibilities of gelcoat cracking in the field. We want to start by talking about cracking in particular, and we want to characterize gelcoat cracks. We need to know what we're talking about and be speaking the same language when we're talking about gelcoat cracking. There are a number of terms that get thrown around that are associated with gelcoat cracking. You might hear the term crazing. People throw the term around stress cracks or spider cracks or that sort of thing. And all of them are descriptive in some sense, but not particularly technical descriptive. So let's talk a little bit about the technical terminology that's involved in gelcoat cracks in characterizing cracks. So we have one flavor of gelcoat cracks that are termed radial cracks. And the two types of cracks that are involved in this particular situation are reverse impact cracks or frontal cracks. So reverse impact cracks, quite commonly known as spider cracks, are formed, as the word implies, from a reverse impact to the laminate, an impact on the back side of the laminate that affects the front side of the gel coat. If we take that exact same impact on the gel coat side of the laminate, it will form that frontal impact, that concentric ring type impact. Well, it's important to understand the difference between the two because it gives you a clue as to what sort of mechanical forces were involved in creating these cracks. So somebody comes to you and they have cracks up toward the bow in the shear section of their hull, and they say, well, you know, I think I might have run into a piling when I was docking or something to that effect. And it looks like a spider crack, something like this. Well, the first thing you want to do is maybe go look in the anchor locker, and you find that the anchor is floating around up front and it's beating up the laminate behind the gel coat. Conversely, if you see this kind of crack, you know that it has been some sort of a frontal impact crack. So understanding these characteristics of cracks gives you an idea of the forces that are involved, and then that directs how you're going to go about doing a repair, or at least what you know about what created those cracks. These are real life shots of reverse impact and frontal cracks. There's another set of cracks, linear cracks, and there's two versions of this. One is a convergent stress field and the other is a divergent stress field. So if we take a panel, an FRP panel, composite panel, and we bend it this way, if it's assuming it's gel coated, if we bend it far enough, it will crack. And generally those cracks will be what are called parallel stress cracks. However, if we have some impact involved while that panel's flexing, we can get this convergent stress field, which is a combination of an impact crack along with a parallel crack. Then we have a divergent stress field, where you will mostly find something like this is where the flow of strain across the surface is interrupted by a structural member. So in this case, if there was a bulkhead running in this orientation across the line of cracking, that interrupts the stress field, and you might get a divergent stress crack. If you look to the inside of the laminate, you almost always find some sort of structure inside that's causing this type of crack pattern. This is a real look at a convergent stress field. We have another set of cracks, linear cracks, parallel stress cracks. Again, if you take a panel and you bend it this way, if it's gel coated, when you bend it to a certain degree, you will start to form these linear stress cracks. If we take that same panel and constrain the edges, for example, let's take the sole of a cockpit, and you have the sides of the cockpit being constrained, but then the sole of the cockpit is flexing, you might see something like these parallel curvilinear stress cracks. So that gives you an idea that the panel is flexing, but you have these constraints on the side, and you look at what might determine that amount of flex. Here are some parallel curvilinear stress cracks. These happen to be going around corners where they're commonly found, and some parallel stress cracking. Another form of cracks is our thermal cracks. When we see thermal cracks, the dead giveaway that they're thermally induced cracks is that they are discontinuous. So you might see these discontinuous linear cracks or random or isotropic cracks. So essentially what's happening here is that as temperature changes, as you go through temperature cycling, hot and cold cycles, the gel coat is expanding and contracting. And when you start to see these types of cracks, it's because of fatigue within the gel coat film. It's expanded and contracted enough that the fatigue starts to show up in these discontinuous crack patterns. It's the same thing if you take a wire coat hanger and bend it enough, it'll break. Well, composites fatigue, and composites fatigue just like that, except it takes a lot longer to fatigue a laminate than it does a gel coat. So whenever you see this sort of thing, generally speaking, it's expansion and contraction over some period of time that has fatigued the gel coat film. Now, this type of crack is also a characteristic of thick gel coat. Thick gel coat, if it's too thick gel coat, over spec thick gel coat, it is much more likely to promote these types of thermal cracks. So whenever you see this kind of cracking going on, you know that it has to do with expansion and contraction. And the very next thing you want to look for is the thickness of the gel coat film that's creating this type of a crack situation. And this is a look at some thermal cracks on some non-skid material. Another type of crack that we have are termed form stress risers. These are stresses that form in around shapes, mostly holes in a laminate. So we have radial stress risers coming out of a round hole in a laminate, or you can find hard point stress risers where you have edges that are fairly sharp. Those edges tend to focus the strain in the laminate. So when you have a square or rectangular hole with sharp edges that's cut through a laminate, as in this illustration, what happens is when there's some mechanical strain on the laminate, that strain becomes focused at the hard points. Therefore, you see hard point risers. This is a shot at a very typical radial riser where you have stress that's forming in that around a hole that would be in the laminate in this case. Now let's take a look at some of the engineering aspects of gel coat and the stresses and strain that it is under when it's in a typical laminate situation. So let's take a look at this sandwich core laminate. This could also be represented by a single skin laminate. It does not have to have a core. I'm just illustrating this because the thickness makes it a little easier to look at. So we have, in this case, two fiberglass skins encapsulating a core material. That core could be any type of core that you'd be inclined to use, whether it's PVC foam or balsa or some type of a honeycomb. And then we have gel coat on the surface. So when we look at the at the strain and stress that's involved in this type of a sandwich structure, what we see is this, that when we bend this, if we bend it in this direction, we'll have maximum tensile strain right at the top of the structure, which is where the gel coat is. And then we'll see maximum compressive strain at the bottom of the structure. So it looks something like this. If you could actually measure the strain directly in the middle of this sandwich structure, it would be 0. That's termed the neutral axis. And the further away you move from the neutral axis toward the tensile side, the higher the strain becomes. And the further you move toward the compressive side, the higher the strain becomes. So unfortunately, the way we use gel coat is we put it in the area of maximum load of a composites panel when we start applying flexural strain to it, or in fact, any type of strain, flexural, resulting in tensile and compressive strain on the laminate. But that's where the gel coat needs to go because of the way we use it in terms of cosmetic qualities. If this is, ridiculous and hypothetical, but if you could put the gel coat directly in the middle of the laminate, the gel coat would hold up much better from mechanical strain because it wouldn't be in that area of maximum strain. But that's not the way it works. So we end up putting the gel coat in the place that creates the highest amount of stress when we start moving this laminate structure by mechanical force. Okay. Let's take a look at crack severity level here. A way of characterizing cracks in terms of the extent of the crack itself. So we look at a partial penetration, which is a partial penetration of the gel coat itself. This is a very fine hairline crack that is not all the way through the gel coat film. Now, one of the reasons why this is important is you need to determine the crack severity level when you're repairing a crack. It's imperative to sand the crack completely out of a repair area in order to make an appropriate repair. So if you have a partial gel coat penetration, the repair can be carried out within the gel coat film exclusively. It doesn't have to go down into the laminate. And then we have a gel coat penetration where the crack is confined to the gel coat film and does not exceed the interface of the laminate. That's also a cosmetic repair that you can execute just within the gel coat film. We have a laminate incursion. This is where this crack goes down into the laminate. Now we have a structural repair. Now we have a repair that you need to grind out the gel coat, and you need to also remove laminate to remove the crack fully, and then put new laminate back in whatever that area is that you've ground out, and re-gel coat in whatever fashion. And then we have a deep laminate incursion, a deep structural crack, something that is associated with structural failure. Now, one of the hallmarks of these types of cracks, as you can see in the illustration, is as the cracks become deeper, they also become wider. So if you're looking at partial gel coat penetration, it's just a very, very tiny hairline crack. Gel coat penetration is going to be a little bit wider. If the crack is wide enough that you can catch it with your fingernail, it's probably into the laminate. Not always, but most likely into the laminate. And if the crack is wide enough that you could say, take the blade of a razor knife and stick the tip in it, it's more than likely pretty deep in the laminate. So understanding the extent of cracks is very, very important to how you're going to go about repairing cracks, whether they're cosmetic, confined to the gel coat, or whether it's structural and you actually have to repair the laminate structure itself. Okay. So if you do a crack repair without understanding the underlying cause, it just begs for the crack to return. So if we take one of those cracks that's the gel coat penetration that's down into the laminate and just do a gel coat repair, the crack will return at some point in time. The whole idea of crack propagation is very real in composites laminate. So what will happen is that crack will propagate back through the gel coat. Same with gel coat. If it's a gel coat penetration all the way through the gel coat, but stops at the laminate interface, and you just do a surface level cosmetic repair on the gel coat and leave some of the crack within the gel coat film, that crack will come back in pretty short order. So when you're doing repairs, it is very important to determine the root cause, and that's necessary for a long-term permanent solution. So if you see something like a spider crack in gel coat and you're going to repair it, you want to have some idea of what's happening inside the laminate that would cause impact force creating that spider crack. Or if you have parallel stress cracks, then the very first question before repair is, how do we stop this panel from flexing? Because if we do the repair and the panel continues to flex in the manner that caused the original cracks, the repair is going to crack anyway. So we have this situation that's involved with discovering the root cause when we're doing gel coat repairs. So let me just take a pause here for a moment, and I want to talk about some sources of information on gel coat cracking. There is an awful lot of information out there, some of it good, some of it not so good. So the sources of information that you use when you're addressing this issue of wanting to learn more about gel coat cracking are important. We have a number of sources of information. So let me just list some, a little bit tongue-in-cheek here, but we're actually kind of serious about this. Sources of information. Well, in our plant, we have good old name your guy, whatever the guy is in your plant. And he's been doing this for 20 years. So in some cases, people use that qualification of 20 years as that makes one an expert. Well, maybe it does, and maybe not. I've seen quite a number of folks who have been at this for 20 years, and they may know how, but they don't know why. That's the important factor here. It's not good enough to know how. You must know why. And when it comes to gel coat cracking, knowing how to fix it may not at all address the problem unless you can address the root cause and understand the why. When I was a kid, my grandfather, who was a wooden boat builder, used to say to me all the time in his folksy way, the guy who knows why will always be the boss of the guy who knows how. Well, the point that he was making was it's important to understand the why that you're doing something. So the fact that you may encounter somebody who has a lot of experience and maybe they are a top-notch gel coat applicator, or they've been around the business, kicking around the business for all of these years, that doesn't necessarily qualify them as an expert in understanding how to analyze gel coat cracks and how to get to the root cause of the problem that's causing the cracks. There are other sources of information. There are many, many self-declared experts online, and a lot of what you will find online and in consumer publications concerning gel coat is nothing more than fiberglass folklore. Each of the publications that you see listed on the screen has published articles or in forums, that sort of thing, and all of them have glaring misrepresentations of what it takes to appropriately fix gel coat, because they know how. A lot of these articles describe how, but they don't understand the why, or they ignore the why part, and they jump to conclusions that are incorrect. So I would implore you, when you're looking for information on composites in general, but in particular, anything to do with boats and gel coat, my broad estimation is probably 90% of what you would discover online is incorrect, because it's coming from a guy who fixed a boat in his backyard. And, all of a sudden he's dispensing advice to all his fellow backyard boat fixers on how to do this sort of thing. So where are sources of information? Well, I saw this the other day and it cracked me up. The general public version of this, you know, there are true experts that have facts and data, and then there are folks who think that they have found more facts and data over and above what the scientists have discovered. This is my Gelcoat cracking version of this. You know, look, I found some information online from a Gelcoat cracking expert. Well, good luck with that. You need to be very, very discriminating about what you read online. I tell this to my IRIS students. I teach the composites technology course at the International Yacht Restoration School in Newport, Rhode Island. And the students are always coming to me with something that they found online. Look at this. This is really a cool idea. You know, this is what this guy says. Or, you know, I had this problem with a mold and I went online and here's what they're saying about it. And the volume of incorrect information that's out there is just staggering. So I would implore you to be very, very careful about what you're finding online, unless you can qualify the source. And if you qualify the source as being a legitimate technical source, then by all means, absorb that information. Okay. So what are reliable sources, prime sources of reliable information? Well, it starts with the product manufacturer. The people who know the most about your gel coat are the people who manufacture the gel coat. They are also a great source of technical information. They have a vested interest in educating you. They have a vested interest in making sure that you know the most that you can learn about their product, because when you know more, their product will perform better, both in the application in the shop and out in the field, and the customers are going to be happy. And if you encounter a problem, you're more than likely to get a better route to repairing that problem when you're dealing with someone who is truly an expert. So that would be the first line, is the product manufacturer. So go to your gel coat manufacturer. Don't be afraid to do that. And if you need to, go to the guys in the lab at that particular gel coat manufacturer. The sales guys, bless their heart, there's a lot of really good ones, and a lot of my good buddies in the industry fall into that category, but they will generally repeat to you what they hear through that particular network. If you go to a gel coat manufacturer and you talk to the guys in the lab, they're not salespeople. They're not PR people. They tend to tell it like it is, in the unvarnished truth. And you'll say, well, you know, I've been spraying my gel coat at 40 mils for a year now. And they'll say, well, you're nuts. 40 mils is unacceptable. You need to bring your thickness down to within range. Where, you know, somebody else might tell you, well, okay, you know, that helps me sell more gel coat. Then there are tech reps in the field. There are folks that are in the field who are from distributors or the product manufacturers. They've been well trained, they're well versed in the technology, and they're rubbing shoulders with people who are well versed in the technology all of the time. They are a good source of information. We then have practitioners in the industry, people who are out in the shops who have some formal training, not on the job training. On the job training, you can't learn any more than whoever's teaching you on the job. So, you know, a company hires a prospective gel coater, and they put them in the booth with the gel coater for a week or a couple of weeks or whatever that time is. And then they learn how to gel coat. Well, what did they learn? Well, they learn what that guy learned and all of his particular habits and so on and so forth. So if you can find industry practitioners who have some formal training, more than likely they have some sense of the proper technical information. You have consultants across the industry, a lot of good folks who have been around for a long time, who really know their stuff. There are industry standards that you can look at for very specific applications, and then industry associations, which publish a lot of technical information. So those are the prime sources of information that I would encourage you to use when you're looking for specific gel coat technical information and what's acceptable and what's not acceptable. Go online at your own peril. So let's take a look at contributing factors to gel coat performance. And some of the items that are the key factors in determining whether a gel coat is going to perform well in the field or not. So we'll look at these areas of gel coat formulation, gel coat handling, application of gel coat, how you're going to apply it, how you're going to spray it, what your habits and what your techniques are. The laminating sequence, mechanical forces that are involved. We'll take a look at environmental exposure. And then there's also consumer maintenance, you know, how the product is maintained and used and so forth. So let's take a look at some of these contributing factors. We start out with the base gel coat formulation. Gel coat is in the form that is mainly used in the marine industry. It's generally speaking a polyester resin or a polyester or vinyl ester resin formulation that is a unsaturated polyester polymer or an unsaturated vinyl ester polymer that is formulated into a gel coat. A gel coat is a resin. That resin has all of the stuff that makes it gel coat, like pigment and some fillers. It has a promoter system that allows it to cure in a very thin film, and maybe a few other goodies. But essentially, a gel coat is a resin that has additives that make it suitable for cosmetic purposes. There are a number of types of gel coat formulations that the industry, the composites industry in general, formulates for different services. There's general FRP service, there's clear gel coats, there's specialty gel coats for cultured marble vanities and that sort of thing. There's gel coats that are formulated for swimming pools. There's sanding primer gel coats. The two that the marine industry most often consumes are tooling gel coat and gel coat that's specifically designed for boats, specifically designed for marine service with that type of application available. So that's what we're going to look at in terms of the formulation. But just in terms of gel coat formulation, there are several things to keep in mind that the gel coat manufacturers have to make determinations on. The gel coat manufacturer is always wrestling with the specifications of the gel coat in terms of everybody wants a glossy product. Consumers like to buy shiny things, and boats need to be shiny if they're going to sell at the boat show. So one way to make a gel coat highly glossy is to make it very hard, and then the gloss level is high. However, if the gel coat is too hard, it tends to crack easier than a softer gel coat. So if you want a gel coat with good durability, a gel coat that has toughness, then it may not have the same gloss as a hard gel coat. So the fine line that the gel coat manufacturers are walking is, how do we make the most highly glossy gel coat we can, and yet it still has the toughness. Technically, that's modulus of elasticity. It has that toughness that it's going to not crack and hold up for the particular service. So it's not a matter of just making the toughest gel coat possible, the highest modulus of elasticity gel coat, or making the shiniest gel coat possible. There's always a compromise in between. And various gel coat formulators make that compromise in slightly different ways according to their testing and the data that they've gathered on how their material is going to perform. Okay. So there's common backbone chemistries that are used for gel coats, from orthophthalic to orthophthalic NPG. We have isophthalic acid, isophthalic NPG gel coats, and then iso NPG, low HAP, low volatile content, which would be low amounts of styrene and or MMA in the gel coat. There are a number of the gel coat companies have proprietary polymers that have been formulated specifically for gel coat. And then we have vinyl esters and some vinyl ester blends. vinyl ester resins that are blended with, say, isophthalic resin to make some gel coats. So there's all of these gel coat chemistries out there that are available. The good part about this is, as a boat manufacturer, your supplier will direct you specifically to gel coats that are manufactured for marine applications. It's not something that you necessarily have to go out and research the polymer chemistry, because those materials are readily available. But in this compromise that I'm talking about in gel coat formulations, it might involve examining these types of properties. We look at elongation percent. So elongation, we're going to pull on a sample, put tensile strain on it, stress, I should say, on that sample. And the elongation is how much does it stretch before it breaks. So you can see that some gel coat formulations tend to perform better than other gel coat formulations. That goes along with the elongation percent, goes along with pretty much closely tied to tensile strength. So the difference here is with the elongation, that's a function of modulus. We're going to pull on it with a certain amount of tension, and how much does it expand? How much longer does it get? Tensile strength is we're going to pull on it until it breaks. So there's some correlation between the two. And then we have Barkle hardness, or the measure of hardness of the material, which is equilibrated in some sense, not directly, but indirectly, to the gloss of the material. So you can see here that some of the highest elongation materials have lower Barkle hardnesses than some of the other materials. So these are always the factors that the gel coat suppliers are working with in order to create a gel coat that's going to be suitable for a specific purpose, like boat applications. So let's talk a little bit about gel coat handling. What happens to this gel coat when it gets in your plant? What happens when it's at the distributor's plant, for example? But very specifically, something that you can control is what happens when the material gets in your plant. So we take a look at this. Right at the top of the list is that gel coat has a shelf life. So what is the shelf life of gel coat? Well, you know, you buy a box of Cheerios at the grocery store, and there's going to be a date stamped on the Cheerios. You know, they're good until 2041 or whatever the particular date might be. And you need to take that into account, or you know, a carton of eggs or whatever it might be. So we've all been faced with pulling something out of the refrigerator and looking at it and going, you know, yeah, you know, it's expired. I'm going to throw it away. It's not that expired. I'm going to eat it anyway. You know the routine there, right? Well, it's more important with gel coat to be paying attention to this. So on the gel coat spec sheet are specifications that are called out by the gel coat manufacturer for a specific gel coat, and it will give you some ranges of specifications: viscosity, fix index, percentage of volatiles, gel time, layup time, so on and so forth. All of those values are the values that the gel coat manufacturer guarantees if the gel coat is within its shelf life. However, when the gel coat exceeds its shelf life, there are no guarantees that it's going to be within specification. Now, if you have a gel coat that has a shelf life of, let's say, 6 months, and it's 6 months and 1 day, is the gel coat bad? Obviously not. But every day it gets further away from that 6 month, every day there is more opportunity that there's going to be changes in that material from the original specification. So paying attention to shelf life is an important factor. What does change? Well, we're dealing with reactive polymers here. And when that material is sitting in the drum or the 5-gallon pail or whatever it might be, it's just not sitting there. There are reactions going on within the polymer all the time. For example, cross-linking occurs when a free radical is created in the polymer chain, or an oxidation byproduct that's in the material. And that free radical will open a bonding site and create another free radical. Well, when that material is sitting in your drum, that process is taking place. It's taking place very slowly, but there's an inhibitor in the gel coat. The way the inhibitor works is the inhibitor is sacrificial. When one of the free radicals is created, the inhibitor reacts with that free radical, and to put it in some kind of terms, both of them die. The free radical and the molecule of inhibitor both die, and nothing happens in the material. Well, as the shelf life progresses, there is less inhibitor to eat up these free radicals. So what happens is, as time progresses, the viscosity of the material, this goes for resin too, by the way, the viscosity will increase and the gel time will change. Generally speaking, the gel time becomes longer. Not always, it depends on sometimes the formulation, but generally speaking, the gel time will become a little bit longer. So if you're using gel coat that is over its shelf life, depending on how far over its shelf life it is, will be some indicator of more potential for changes in the material from the original guaranteed specifications. Now, one of the other things that's involved with shelf life is storage temperature. If you're storing material in elevated temperatures as compared to cold temperatures, it makes a difference. So if your gel coat is stored in an outside lean-to in Florida during the summer, it's going to be way hotter than somebody who has their material stored in a lean-to in Minnesota. The stuff in Minnesota is going to last longer within specification because the temperatures are not as high. So the shelf life is important to pay attention to, and that involves inventory management in your plant. You want to make sure that the oldest material is always shuffled to the front of the pile, so that you don't run into a situation where you're using the new material before you use the old material. So it's the old inventory thing: first out, first used, or first in, first used. And don't make sure you don't get caught with material that is aged out, because it's more convenient to use the drums in the front or something to that effect. So shelf life is an important aspect of managing the ability to get the highest quality out of your gel coat. We'll talk a little bit about gel coat storage temperature. Low temperatures have no effect on shelf life. So when we're talking about low temperatures, let's use room temperature, a 70-degree room temperature as the baseline. So lower temperatures have no effect on shelf life and actually can preserve the shelf life as the temperature gets lower, whereas high temperatures reduce shelf life. So if you had black drums and they set outside, the black drums are going to heat up, and all things being equal, the shelf life of that material won't be as long as the same material that was stored indoors. If drums are stored outside in cold conditions, if you don't happen to be in Florida and you're somewhere in the Northeast or the upper Midwest or something to that effect, and the material was stored, say in a building, but an unheated storage building, it can take 2 to 3 days for a drum of gel coat to warm up to room temperature. So if you bring a drum of gel coat in, say 40 degrees, and you try to spray it, what's going to happen? Well, the viscosity is going to be really high. It's not going to spray right. All kinds of bad things are going to happen with trying to apply the gel coat. And it's not a matter of the temperature of the gel coat on the mold. The temperature of the gel coat on the mold is very quickly going to become mold temperature, but it's a matter of getting it out of the spray gun, trying to spray this high viscosity material to ensure that the initiator mix is appropriate, and so on and so forth. So the pros and cons: stored in cold weather, the shelf life is longer. and the material will be more stable. However, you have to make sure that you bring it up to room temperature before you spray. In addition to that, gel coat that's been sitting around for a while tends to phase separate. Phase separation from a technical standpoint is not exactly the appropriate technical term, but gel coat doesn't fit into the technical terms. There's another term called gravity separation that essentially separates heavier and lighter components. Well, these materials kind of fall into an interim definition of the technical definition of phase separation, gravity separation. I'm going to use phase separation because I think everybody knows what we're talking about here. So essentially, if you have a drum of material or a 5-gallon pail or a gallon can, and it's sitting there long enough, what will happen is that you will get this separation. The light fractions will float to the surface. So that consists of styrene and or methyl methacrylate. If it's a gel coat, a lot of them have methyl methacrylate in as a secondary monomer, and the promoter. So if you open an open top gel coat drum that's been sitting around for a while, you're going to see a pinkish liquid on the surface. So that pinkish liquid is, generally speaking, the cobalt and or DMA promoter, and styrene or that combination of styrene and MMA that's on the surface. Now, if you think about this, if all the light stuff is on top, where'd all the heavier stuff go? Well, that's very obvious. The heavier stuff is at the bottom, and the more light stuff on top, the more heavier stuff on bottom. So in this drum, in those mid fractions, you have the polyester polymer that the styrene, the monomer, has separated from. And down at the bottom, you're going to have a higher concentration of pigments and fillers. So what's going to happen if you try to spray this stuff without properly mixing it? Let's say you don't mix it, which is the absolute worst case scenario, or you don't use the proper mixing equipment or don't stir it long enough. Well, as you start operating out of this drum, you're going to be spraying these heavier fractions, I should say. So you'll have the spray gun set up. You'll have the spray gun pressure will have to be cranked up. You might need to use a larger spray tip, or the spray pattern's not going to be that good. And as you work your way down in the drum, the viscosity is going to become lower and lower, and the material's also going to become more reactive. The gel time is going to get shorter and shorter. This is really bad news if you're using material that's not properly blended, or you're not blending it with the proper equipment in order to get a homogeneous mix. You need to be able to literally turn over the drum from top to bottom in order to get the appropriate mix to blend this phased separation of materials. So in mixing gel coat, if you are mixing a 55-gallon drum, the ideal mixer to use is one of these wide blade mixers. These things generally turn at maybe something like 60 RPMs. They're fairly slow. They kind of gently blend the gel coat, but they have the capability of turning over the entire drum. They will pull the material up off the bottom, and they will shove it up to the top, and the top material kind of works its way, downdrafts its way back down to the bottom, so on and so forth. So a mixer like this is very, very effective. And in fact, this is the mixer that you need to be using if you're using drums of material. The little bunghole mixers, the ones with the folding blades or the screw type mixers, they mix the gel coat, but they're not particularly effective in turning over the entire drum. So if you had gel coat that was pretty well blended to start with, one of those little bunghole mixers might be enough to keep it in the appropriate phase blending, if you will. But if the drum's been sitting around for a while, they are not at all adequate to turn over the entire drum. I worked as part of a team on a legal case with a manufacturer who was involved in some rather large-scale legal proceedings involving Gelcoat. And it turned out that they were getting their Gelcoat in 300-gallon tote tanks, a pretty large manufacturer, and these 300-gallon tote tanks, and they were using one of the little bunghole blade mixers to mix it. Well, the bottom line is they never got that 300-gallon tote tank mixed. And when we started going through all of the data and correlating the data, you could actually track the defects from the first use of the container when all the heavy material was on the bottom to down to the bottom, or draining the last stuff off the top with the light viscosity. So the bottom line is you really need one of these blade type drum mixers. Now, if you said to me, well, I don't know, those things are pretty expensive, I don't know if I can afford one of those, I will guarantee you, if you have one quality defect and have to fix it, you can afford one of these. You will have spent much more money on fixing a defect out in the field than this drum top mixer will ever cost you. So, my advice is, yeah, it costs a lot of money, but not anywhere near as much money as having defects out in the field. If you're mixing a 5-gallon bucket, I've seen on many occasions, guys in the shop, they grab a stick from the floor and they start stirring this 5-gallon bucket. You really can't mix a 5-gallon bucket with a stick. You need a power mixer with some sort of mixing device on it in order to mix that 5-gallon bucket. My strong recommendation is attach that to either an air motor or a cordless drill. Don't use a corded drill. Over the years, I've seen 2 guys catch on fire mixing materials with a corded drill. So it would, it would be appropriate not to do that. So 5-gallon pail requires a power mixer. A gallon can or less you can mix by hand, but with a gallon can, you have to mix it a lot more than you think you have to mix it. It probably takes close to 5 minutes to actually turn over a gallon can mixing it by hand. So, you know what happens when you go to the paint store and you buy some latex paint to paint your living room, right? They put it on the shaker, right? Can you mix it by hand? You can, but it won't be nearly as well blended as if you put it in the shaker. So my advice to you is make sure that your gel coat is 100% thoroughly blended before you use it, because all sorts of phantom problems can occur with gel coat if the viscosity is uneven, viscosity or consistency from the top of the container to the bottom of the container. You really need to pay a lot of attention to proper mixing. Okay. With mechanical mixing, air-powered mixers are always preferred in a composite shop. If not, a battery-powered drill or something to that effect is okay. And as I mentioned earlier, not plug-in electric. That's not appropriate for mixing any of these materials that have styrene, or in particular MMA monomer, which is rather volatile. Now, in mixing gel coat, the rule of thumb is mix for at least 10 minutes. This is operating under the assumption that you have an appropriate mixing device that can turn the drum from the top to the bottom. So you've circulated the entire drum of material or 5-gallon pail of material within those 10 minutes. So mix it for at least 10 minutes within every 24-hour period. So if I mix gel coat right now, I can spray it tomorrow morning. But if I'm going to spray it at 5 o'clock tomorrow, I need to mix it again. 24-hour period. Or see the little caveat down bottom, or according to the manufacturer's recommendations. There are certain gel coats that the mixing recommendations might be something different than 10 minutes in a 24-hour period. Clear gel coat or a metal flake gel coat or something to that effect. So whatever the manufacturer says, they will have some specific recommendations on how to mix their material. And that's the appropriate way to go to make sure that your material is perfectly blended. If it's not well blended, you can expect top performance out of the material when it gets out into the consumer's hands. Okay. So let's talk a little bit about gel coat application. And what we're going to talk about here is application in relation to gel coat cracking. Okay, so influences on cracking. With application, we have film thickness at the top of the list. How thick is the gel coat? The initiator level, shop temperature, and then the timing of the laminate that's going to go behind the gel coat. All of these things kind of conspire together to either make the gel coat perform really well or contribute to some cracking issues and product reliability or customer perception issues. Okay, so film thickness. Gel coats are made as an in-mold coating, meaning that they're specifically formulated to be sprayed in a mold, and then the laminate is applied behind the gel coat in the mold. And they are specifically formulated to be sprayed in a pretty narrow range in a thin film thickness. For most gel coats, again, see the little caveat down here, refer to the manufacturer's specifications for a specific gel coat. That always trumps any other recommendation. But the Goldilocks zone for most gel coats is somewhere between 18 and 24 mils wet. This is measured with a wet film gauge, a mil gauge. That 18 or 24 mils wet is going to cure to 13 to 18 mils. This is in a cost estimator that I use. This is a table that you enter the monomer quantity in the gel coat, monomer percentage of the gel coat, and it will give you the wet film at a wet film thickness, what the dry, I should say cured film thickness will be here. And then the amount, the percentage of film thickness retention. So in this particular case, the film thickness retention is about 74%. So in other words, you're losing 26% of the thickness of the film during curing. Why is that? What's causing that? Well, at the top of the list is styrene and or methyl methacrylate, MMA, evaporative loss. You have the styrene and MMA leaving the system in emissions, and that is volume that's leaving the system. And then there is the polymer shrinkage during cross-linking. So you have the polyester or vinyl ester polymer, and then you have the monomer polymer. And when they cross-link, when those reactive sites bond, they actually pull closer together. So you have the volumetric loss from polymer shrinkage, and then you have the evaporative loss of styrene. So if you spray the material under thickness, then the cured thickness is going to become a problem because you're losing the 24% of material from wet to dry. So film thickness in general is a major issue with gel coating. Again, manufacturer's recommendation trumps every other recommendation, but you may have a film thickness that works for you in your particular application. And if you get outside of that range, things happen. If the gel coat is too thick, cracking is right at the top of the list. Too thick gel coat is a prime cause of gel coat cracking. And why is that? Well, because of what we looked at before. Gel coat is at the place of maximum stress in the laminate structure, and gel coat is not reinforced. Gel coat has a lower fatigue strength than the underlying laminate does. Gel coat that's too thick also tends to yellow, and it also tends to produce more porosity than thinner gel coat does. All of those things are not good. Gel coat that is too thin, that is under specification, exhibits poor cure. Now, why is that? Why? Well, let me go forward from here. It also exhibits poor gloss and poor weathering. They're actually attributes of a poor cure. So why does too thin gel coat not cure correctly? Well, the reason is that you can have gel coat thin enough that there is so much loss of styrene emissions or monomer emissions, there's not enough styrene left to cross-link in the system. The evaporation from a gel coat film is based on surface area. So if we have gel coat, stick with me on this. Over here, we gel coat at 20 mils thick, and over here, we gel coat at 10 mils thick. And then during the course of these two thicknesses curing, they lose a certain amount of styrene based on surface area. They both lose the same amount of styrene. However, percentage-wise, that's twice as much styrene loss from the 10 mil gel coat as it is from the 20 mil gel coat. So as gel coat gets to be thin, and the thinner it gets, the worse it becomes, there may not be the mechanism for a complete cure of the material. As the styrene loss exceeds a certain amount, there's simply not enough styrene molecules or reactive sites available to react for cross-linking. So when gel coat gets thin, it's generally speaking undercured. Now, when we're talking about undercured, I'm not talking about it's going to be wet when you touch it. It'll cure, you'll get a laminate on it, the part will come out of the mold, but the barcode hardness may be low. And the worst part of it is when you get it out in the field, once it's out of your hands, once it's into the customer's hands, once the customer becomes the one making the judgment on how it performs, it leads to poor gloss or degradation of that gloss and poor weathering. So a white gel coat will tend to turn yellow or tannish over a period of time. Dark color gel coats, dark blue, red, something like that, they become lighter in color over a period of time. So gel coat thickness is exceedingly critical in extracting the maximum performance of the gel coat the way it's designed to be used. Here is an example of thick gel coat that is really extreme. You can see the cracks on the side of this hull, and this is after those cracks are ground out. Now, in this particular situation, the boat owner was obviously concerned about these cracks on this particular hull, and the fact that the cracks a few years before that were just starting to appear, and there were a few of them. And over the intervening couple of years, the cracks just became greater and greater. So he had one of the guys at the marina start to Dremel out some of these cracks. Look at the thickness of the gel coat here. You look at it here. We're looking at gel coat that you can measure in 1/8 of an inch, not in mils here. Well, it's no wonder that this thing cracked. In fact, all over the entire boat, the gel coat was mega thick, like we're looking at here, and the entire boat was full of cracks. So not at all surprising when you see something like this. And this is an extreme example. But if the spec on the gel coat is 18 to 24 mils, and say the gel coater doubles up in corners, for example. So they spray the proper 18 mils in a flat and in the corner, and then they spray the next panel down into the corner. They might have 18 mils and 18 mils and 36 mils in the corner. It might not look too much different than this if the spraying techniques aren't refined enough to produce the same thickness of gel coat in those overlapping areas. So you need to be careful about thickness buildup in tight places. Another place that's very common for thickness buildup is if you look at a fly bridge. You're looking at, imagine, take that fly bridge now, flip it upside down and put it in the mold. And what you're looking at is this deep well down in the mold. You know, it's like this wide, and it could be, 24 inches deep, maybe even a little deeper on a bigger boat. And you have to get the gel coat down in the bottom of this well. There's not a great way to spray that. So in order to get the right amount of gel coat on the sides of this deep well, you're spraying at an angle up here. What happens is it tends to load up the bottom. So if you look at the I don't know, I'm going to call it the rub rail area, the top edge of a flying bridge, a lot of times the gel coat is over thick and tends to crack in those specific areas. It's a place where you find cracks on a routine basis. So gel coat thickness is very critical to the performance of gel coat and preventing cracking. We then have initiator ratio and mixing are important. You know, how much initiator are you putting in the material? How much MEKP is it? And next is it thoroughly blended? So we have two things going on here. Let's say you're diligent and you calibrate your spray gun on a routine basis, and you know how much initiator, sometimes called catalyst in the industry, right? You know how much initiator you have at the gun head. The next question is that equally distributed across the spray pattern? So you could run into a situation that looks something like this. Let's say you're spraying at a target of 1.5%. And you have 1.5% back here at the spray nozzle when you calibrate the spray gun, but the distribution in the spray pattern is not correct. So you end up with 3% here, and you have fingers at the edges of the spray pattern that may have no initiator in them or very little initiator. So as you spray, each spray band has a section that's over initiated and under initiated. Bad things happen when that occurs. So it's really, really important to make sure that your initiator spray pattern is exactly right. I did an experiment one time. It might be something that you want to do. It involves a little bit of a hassle, but I took white gel coat and sprayed with red MEKP. Now that creates an unattractive pink gel coat, but I wanted to see where the initiator was going. And I have to tell you, sometimes it's shocking to find out exactly where the initiator is going. You can't see that when you're using clear MEKP that you would use with gel coat. You might want to try that as an experiment. If you're thinking about buying a new piece of application equipment, you might want to try that out to find out if that equipment supports a very even distribution of initiator across the surface. But it's a real eye-opener when you put the red MEKP in the gel coat just to see where it ends up. So the two issues here are the right percentage of MEKP, and there is an a very distinct upper and lower limit that you can use, and then the proper distribution across the spray pattern. Okay, so the acceptable range is typically for gel coats 1.5%. Some manufacturers ask for 1.75 or 8% as the minimum, up to around 3. Maybe in some cases you could go 3.5. So this is the acceptable range. The gel coat manufacturer will tell you what that is or recommend it. If you ask them, if you ask them for the upper and lower limits on 9% active oxygen MEKP, you will get whatever that happens to be. I also might mention to you that if you happen to be one who uses the summer catalyst, the 5% active oxygen, you are at great peril for permanently undercuring your gel coat. Yeah, it'll get hard. Yeah, you'll get the part out of the mold, but the cure won't be thorough. Those summer blend initiators have less active oxygen in them. So if you are spraying at 1.5% normal 9% AO MEKP, and then you switch to the summer blend at 5% active oxygen at 1.5%, you have a little bit more than half. So you're down at now 0.8% active oxygen in the system. Your gel coat's not going to properly cure. It'll again, and when I'm talking about that, I'm talking about reaching the ultimate hardness and the ultimate weatherability. So you want to be very careful about using those summer blend initiators. If you are using a summer blend initiator, you, rather than spraying at 1.5%, you have to spray at something like 2.8% to get enough active oxygen. So be very, very careful about that. But there is a distinct range, which is the point that I'm trying to get at here, that will be recommended by the gel coat manufacturer. A phone call to the guys in the lab. What initiator do you use in the lab, and what is the percentage range that you use? Is where you want to get that information from. Okay. Too much initiator will cause curing problems. If you really go crazy with initiator, what happens is the initiator starts reacting with itself. and it starts eating up that active oxygen, and it will actually foam. It will actually create porosity in the system. That's if you overdo it, or if you use the wrong initiator, it'll do that too. There are some initiators that are formulated, they manipulate the monomer dimer ratio in the initiator. Some are formulated for vinyl ester resins, others are formulated for polyester resins. If you get the wrong initiator, you can have that kind of problem. But too much initiator can cause curing problems in the sense that, yeah, it's going to cure very quickly, but you might also have porosity, and you might end up with poor weathering because of too much initiator. One of the things that I do that we kind of have fun with the students in the IRIS Composites Technology program is we go to a boat show, typically the Newport, Rhode Island boat show, which we just did last week. And they have assignments. They have assignments like identify the size of the sanding block that was used to make the plug, to make the mold, to make the hull that we're standing there looking at. And you can identify on some hulls whether they used a long block or a short block because you can see the segments around the hull. That's one little fun thing. But the other thing that we do is we walk around and we look at brand new boats, high dollar boats, and we pick out the patches on the boats. And when we're picking out the patches, their assignment is to assess whether that patch is over-initiated, too much initiator, whether it was thinned with acetone or whether it's thinned with styrene. And we can pick out the nuances in the patches once you've seen this, once you understand what it is on brand new boats. We always have to run off to the side away from the salespeople to discuss this because it's it's bad etiquette to be talking about the boat in front of customers. But when the gel coat is thinned with either styrene or acetone, or when too much initiator is used, in many cases, you can identify that specifically. Too little initiator, curing problems. It's not going to cure very well. It's going to say the barcode hardness is going to be low. That will present long-term gloss problems. The gloss will not hold up well, and poor weathering. So we have all of these things that are involved with too little initiator. In the shop, shifting gears here, in the shop, there are some important temperatures that have direct input into the efficacy of the gel coat cure. And that is when you're applying gel coat, when you're spraying, the mold temperature, the gel coat temperature, and the ambient air temperature. All of those temperatures need to be up to a minimum temperature range. 70-ish is very ideal for this sort of thing. But if you're spraying cold gel coat, the gel coat set overnight in a cold area in the plant or something like that, the viscosity is going to be high. It's not going to atomize as well. You don't have to worry about the temperature of the cold gel coat when it gets on the mold, because by the time, if you spray gel coat, say the room's 70, you spray 60-degree gel coat, by the time it's atomized out of the gun and gets on the mold, and then the mold's 70, it will be 70. The problem is getting it out of the gun to start with. But then the mold temperature is another story. If you have a cold mold, let's paint a scenario. You're in one of the northern climates and you have a mold that's outside or stored in an unheated building or something like that, and you pull it into the shop and the mold is 50 degrees and your gel coat and air temperature is 70 degrees. When you spray the gel coat on that cold mold, what temperature is the gel coat going to cure at? Well, not 70. It's not going to cure at the air temperature. It's going to cure at the temperature of the mold, because that very thin film of gel coat is sitting on that large mass of a mold. And then, of course, there's the ambient air temperature. All of those temperatures are important contributors to the overall curing and performance of the gel coat. So there's an ideal temperature range for gel coat, and then there's a technical temperature range for gel coat. So the ideal temperature ranges are what's referred or preferred in kind of a real world scenario. We prefer, that this is the parameters that we would work in, and we can work in those parameters. And the technical temperatures are possible if you apply yourself, if you make an effort to produce the best quality gel coat possible. So what that looks like, the ideal temperature to spray, I got that backwards, by the way. The ideal temperature is what you're really shooting for. The technical is what is the range that's practical. Excuse me for mixing those two up. So the ideal temperature for gel coat would be that the mold, gel coat mold and air would be between 70 and 85 degrees. Well, that's great if your shop is there sometimes. So let's throw this on the table. Polyester gel coat does not cure well at temperatures below 60. If you get below 60, you're not going to get the cross-linking density that you would get at 65 or 70. It simply doesn't cure well. And that's polymer chemistry. Time does not take care of that. If it sits on the mold and it cures, it gets to the point where the film reaches peak exotherm, that point where the reaction starts to slow down at below 7 or below 60 degrees. Even if it sits there for a week, it's not going to be that much more cured. It's that initial cross-linking that counts. Now, 85 degrees. We know that we work at hotter than 85 degrees. Here's the key to that. You can only go down to the minimum acceptable initiator level. You cannot go any lower than that. So as the temperature becomes higher than 85 degrees, the question is, can you handle the gel time of the material without breaking the minimum initiator level? So you're down to whatever the minimum is, 1.8%, 1.5% for gel coat. And it's 95 degrees in the shop, but the material is gelling so fast that you're getting alligatoring problems when you come back and cover an area and that sort of thing. What do you do about that? Well, you cannot drop the initiator level any lower. If you drop it down to 1%, say, then you're going to have long-term weathering problems. So the limitation on high temperature becomes what you can handle at the minimum initiator level. That's not to say that you could not spray gel coat at 100 or 110 degrees. As long as you can handle the material at that minimum initiator level and not go any lower than that. So we've got a couple hard lines here when it comes to gel coat temperature, never below 60 degrees. And interestingly enough, the places in the country where they have the worst problem with this are not places that you would suspect. The places with the worst problem was below 60 degrees are Florida, South Texas, and the Southwest United States, because there's a lot of shops that don't have heat just because of that environment that they're working in. No one in Minnesota has a problem with this. If you have a plant in Michigan, you have heaters and the heaters are on and you would never let the plant go below 60 degrees. So the northern climate or people, I should say, people that run shops where they're heating the shops don't have this kind of problem, but it's a greater problem in some of the southern areas where shops are not heated. Doesn't matter whether it's going to be 85 degrees later in the day. If your mold and your air temperature are at 60 degrees, that's what your cure temperature is going to be. Or if they're, heaven forbid, at 55 degrees January in Jacksonville or something to that effect, you've got a problem when that occurs. Okay. Now, let's talk about the gel coat laminate interface bond. This is the timing of the laminate. So we've sprayed our gel coat. We have the perfect middle thickness and it's the right temperature and all those good things. The gel coat is on the mold and the gel coat is curing. We have a time window in order to get back on the gel coat and laminate. And that time window is generally pegged at about 45 minutes to 3 hours being ideal. You might be able to extend it out to say 6 hours, something like that. Ask your gel coat supplier. They will have done some testing with this. So what happens is this: if you let the gel coat cure too long before you put the laminate on it, you have a gel coat state of cure that doesn't allow for a highly effective interface bond between the gel coat and the laminate. In other words, the laminate doesn't stick to the gel coat as well. So you have the state of cure of gel coat. Now, that's not always associated with clock time. You know, it might be one thing in your shop. You say, okay, here's our procedure. We'll gel coat, and 1 hour later, we're going to laminate because it'll be cured then. Well, that depends on the temperature in the shop and all those temperature parameters that we talked about for curing, and on the initiator level. So that timing may not be the same in August as it is in January in your plant, of when it's okay to laminate behind the gel coat. Now, there's two parameters that we face there. One is if you laminate too soon over the gel coat, things get messy. Sometimes the styrene and the laminate will tend to start pulling some pigment around with it and that sort of thing. But the other thing is, if the gel coat's soft at that point, you might tend to get some printout if it's kind of co-curing along with the laminate. So that's too soon. There's more danger actually in letting the gel coat go too long. If the gel coat is in an advanced state of cure, when you put the laminate on it, you may not get a good interface bond. So typically that is, the rule of thumb is this: you would never let a gel coat go overnight. You would never let it cure overnight before laminating. If you gel coat in the late afternoon, evening, and go home and then come back and laminate the next morning, the gel coat is more than likely in a state of cure that the bond between the gel coat and the laminate is not ideal. Now, the ramification of that is now we're going to apply some mechanical force to this thing that's used out in the field, gel coat cracking. It will exacerbate gel coat cracking if the gel coat is too cured when the laminate is applied. So let me give you an example of this. Some years ago, I worked on a consulting project with a truck cap and van top manufacturer in the Midwest. And they were producing large volumes of truck caps and van tops and had a good reputation, and business was good. And seemingly almost all of a sudden, they started ending up with cracks in these van tops. Dealers reporting cracks before the vans were actually sold to the buyers. And things like that were happening. They had hundreds of vans out in the field that cracks were being reported. They never had that problem before. It was just something that suddenly happened. And this was a big dollar deal, because what would happen is that these van tops were all painted the same color as the vans. So they were shipped with a primer gel coat, and then they would be painted by the van converter. So now you got a big deal. Now you've got this top that's got cracks. It needs a gel coat repair, and the paint has to be matched. The whole thing has to be repainted. Lots of dollars floating around here on this particular issue that was happening. So as we dug into it, I started looking at data, and I was correlating when these things were made and the time of day they were made, so on and so forth. And it jumped out like the biggest red flag that you've ever seen was all of these tops that cracked were started on a Friday afternoon. What had happened was they had a best gel coat practice in place, but somewhere along the line in production, it was assumed that if they could gel coat a whole batch of molds on Friday afternoon, first thing on Monday morning, the guys could come in and start the laminate. All of these, well, 99% of these tops that cracked were built that way. The gel coat went on Friday afternoon, they set all weekend, Monday morning, they came in and laminated. As soon as they stopped doing that, as soon as they got back to their 45-minute to 3-hour window, the cracking problem disappeared. So that's how critical that is in terms of the gel coat to laminate interface. Basically, if you're going to gel coat something, you need to have the time in the day to get at least a skin coat, a pre-laid laminate down on top of that gel coat so that you don't have the problem. Now with laminating resin, you don't have that same issue because it's not made to cure like a laminate. If you get a skin coat on a Friday afternoon and you come in on a Monday, you just scuff it. You just, kind of quickly grind over the surface and you're good to go. It's a little bit of a different situation there, but with gel coat, that timing is very critical. Okay. Here's an example of, this is that same boat that had the giant thick gel coat. It also had a really bad bond to the laminate. You can see up in here where the gel coat is actually pulling off the laminate. And you can see that there's not much bonding that has gone on in this area. So that's a critical issue. Okay. So bear with me for 1 second here. Let's see where we are. Starting to get a little bit tight on time here. I want to talk to you real quick about some engineering terminology that's associated with Gelcoat cracking, so that we're not using street terms. Now, if I said to you, I want you to make something strong, what would that mean? Now, well, strong is not a technical definition in engineering sense without some descriptors attached to it. So we have some descriptors that are attached to Gelcoat cracking. So we'll look at force. Force is an action that alters the motion of a body or distorts it. And it's a measure of the amount of energy that's applied on this body. Then we have stress and strain, and these terms get used interchangeably and sometimes not in the right way. Stress is the amount of force applied per unit area. So force is the amount of motion that the body distorts when this force is applied, and stress is the amount of force per given area. It's a measurement. Strain is the amount of deformation. How much is it going to move? Then we have this description of strength and modulus. Strength is the amount of resistance of an object that an object exerts, resistance that it exerts to force before it breaks. Okay, so we load this panel and it bends and bends, and at some point it'll break. Just before that is maximum strength. And then modulus is the amount an object deforms with a given load. So we take two materials. We take a stiff material and a flexi material, and we put a load on it. We put 500 pounds on it. And this one bends this much, and this one bends this much. That's modulus. Okay, it's a comparison of the flexure in relation to the load in this particular case. So when we start talking about Gelcoat cracking and we start throwing these pieces of terminology around, it helps when we're using the appropriate engineering terms. And just to go through these real quick, flexural strength is force that acts perpendicular to a surface. That's flexure. So we talk about a panel flexing, the panel is doing this sort of thing. Tensile is force that's going to lengthen an object. Compressive is force that's going to try to shorten an object, and the resistance to that force is compressive strength. Impact strength is a force that acts perpendicular to a surface, but in a localized area. You know, you run your boat into something, that's an impact situation. And then shear strength is shear stress acts parallel to the surface, pulling a surface apart. So when we're talking about sandwich panel, the chord panel, and we have a top skin and a bottom skin, and then you have core in the middle, we talk about the shear strength of the core. What is the ability of the core to hold those two skins in relation to each other so that the skins don't move? That's shear strength. Okay, so those are the engineering properties that we're talking about. And then we have fatigue strength. Fatigue strength, we're going to take this thing and we're going to bend it until it fatigues and fails. So it's the result of stress that acts repeatedly, deforming an object. Some other influences on cracking. We have environmental conditions, solar radiation, UV. We're going to talk a little bit about that in a moment. We've talked about thermal stress, just normal temperature changes, normal day-night temperature changes, the movement that's involved in the laminate, or a skin in a laminate or something to that effect. Back many moons ago, in my Viking Yacht Company days, before Viking built the new plant that they operate in now, the hulls would go up the assembly line and the decks went outside. And in the winter, when a 40-foot deck was brought in and set on a hull, it would be an inch shorter than the hull if it was cold out. And they would basically have to let the deck sit there overnight, and then the next morning the deck would fit. So in 40 feet, there was about that 1 inch of movement, the coefficient of thermal expansion. That's causing stress. And even minor temperature changes, 10 or 15 degrees, there's a small amount of movement that's going on. So you could take a boat and you can cover it up and you can put it in an enclosed shed, and there is still stress on the gel coat, as long as there's temperature change. Physical stress, obviously, whatever mechanical stress is working on it. And then when you get cracks, the effect of water vapor. If you have cracks and it freezes in the northern climates, that becomes somewhat of an issue. Let's look at UV degradation of gel coats. And we're just going to touch on this for a second. We could spend an entire week on this subject. We have UV, which is a wavelength of solar radiation. And it's this UVB wavelength that tends to become a bit of a problem for us. The UVA, the UVC is filtered out by most of the atmosphere, and UVB is filtered out by window glass, but not by the atmosphere. And then UVA affects polymers. So it's somewhat of the UVB wavelength, this 315 to 280 nanometers, and then the UVA wavelength that affects it. There's two effects of UV radiation on gel coat. One is photooxidation. That is, you know what an oxidized paint looks like, an old car, you know, that 1970s boat sitting in somebody's backyard, the red boat that's now pink and nasty looking, that sort of thing. Well, what happens with oxidation is, if you look at the surface, a gel coat or a paint surface, under magnification, it's not perfectly smooth. There's little peaks and valleys. And photooxidation is where these little peaks slough off. The UV degrades the material, and little microscopic pieces of the material slough off and create that white powder that you see in a severely oxidized part. And then there's photoinitiation. UV acts as an initiator. So if you have some unreacted cross-linking sites on the surface or just below the surface, the UV will react those sites, but it generally reacts styrene to styrene. So those are cross-links that are not as strong. They're not as robust as the styrene, the polyester cross-links. They tend to turn yellow. They tend to get brownish in color. So those effects of UV radiation are going on with gel coat all the time. If you have a boat that is obviously gel coated, and you have that same gel coat, you saved the gel coat from the batch that you made the boat in, and you patch it with that batch of material after it's been outside in the sun for a couple of months, it's probably not going to match anymore. The same thing happens on cars. That's why when you get a ding in your car door, the body shop won't just fix the ding because they can't match the paint exactly. They'll paint the entire door, they paint the entire panel. Well, that happens with gel coat too. So the effects of UV radiation are something that affects gel coat. The bottom line with this whole thing goes back to how critical was the application of the gel coat and the curing of the material. If your application is correct and it's properly cured, it performs better under this UV exposure than it might not be otherwise.